Hello, my name is Pascal, and I will be talking about our work, FoggySight, a scheme for facial search privacy. So this work is joint work with Ivan Eftimov and Yoshi Kono, and it was done at the University of Washington. So this work is about face recognition technology and proposing to use adversarial examples to defend against face recognition technology. And to understand why this is an important problem overall, we have to understand a little bit of background about face recognition. So for those who don't know, face recognition is the use of computer vision and machine learning algorithms to automatically detect who is in a particular image. These days, face recognition technology mostly uses deep learning. And because of modern compute power and sort of the rise of larger and bigger deep models, face recognition has gotten very, very strong. It's gotten very performant in the last couple of years, to the point that it poses a threat to individual privacy, right? If people can identify you from just photos they take of you on the street, any stranger could look you up, and you can see why this can be a problem for your personal privacy. It can enable, stalking behavior. It can be used, it can be abused by law enforcement in criminal cases or by the government to crack down on dissent. So there's a lot of reasons why we want to be careful about face recognition technology and why we might want to find ways to protect our own privacy against this, right? There have been a lot of news reports recently about the subject, about why it's important to protect one's personal privacy against technology like face recognition technology. So hopefully that statement is not so controversial. So basically the way that this technology works, in very brief, is you have some query photo of a person you're trying to identify. You run them through a face recognition model, which then produces an embedding in n-dimensional space. And this embedding has the property that photos of the same person tend to cluster far away from photos of other people. So photos of the same person cluster into distinct clusters in n-dimensional space. This embedding space is produced by a deep neural network, and then a k-nearest neighbors classifier is usually run on top of this photo to determine, given the query photo, which is this dark blue photo, and the lookup set photos, which is all these other photos in the embedding space, who is most likely to be depicted in this photo. So you can see that a k-nearest classifier in this case is very accurate. So we propose to use adversarial examples, which are small perturbations in images that sort of fool deep learning models to attack face recognition systems. And in order to get there, we need to understand the goals of our scheme of using adversarial examples. The first of which is privacy. So obviously we want to fool a face recognition system. We want to make sure that that system cannot identify us in our query photos. Two, the goal is to not actually degrade the quality of the photos that we are changing. So if we modify a photo of you that you put on social media or that you have online of yourself, you want to make sure you're still happy with that photo and that photo is still useful to you as a human being. And finally, we want to make sure that it's not immediately obvious to an automated detection system that this photo is some adversarially modified photo, right? It's picked up by a face recognition company and put in their database without them knowing. So there's a lot of actually related work on this subject about using adversarial examples to attack face recognition systems. Sharif et al. Talk about using physical adversarial examples to protect one's privacy, and those adversarial examples are sort of in the form of glasses. Shan et al., a more recent paper, proposed a system called Fox, which uses pixel level changes to sort of attack the training set using data poisoning. So there are a lot of similar papers on this work. And hopefully, as we keep going through the presentation, we highlight what makes our paper unique. And of course, there are other papers that we don't mention on the slide. For the full list of related work, I encourage you to see our paper. So to talk about these kinds of privacy protecting schemes, we need a way to determine, okay, how good numerically can we quantify the performance of a privacy protecting scheme? How good is it at actually protecting our privacy? So we introduced 3 different metrics to sort of quantify this. The first is the recall rate. So if we have some query photo, which we embed, and we use the deep learning network, and we get 100 closest photos to my query photo, the recall rate asks how many of those photos are of the query photo. So if you take a photo of me and you run it on your face recognition model and you get the top 100 matches, the recall rate asks what percentage of those top 100 matches are me. So if I appear in 70% of those photos, the recall rate is 0.7. The discovery rate is a stricter metric than the recall rate, and it asks how often do I appear at least once in the top K lookup set. So if you take a query photo of me and you run it against your database search, and on average with different query photos of me, I appear in the top K set 50 or 60 or 90% of the time, at least once, even once in the top K nearest neighbors. That's the discovery rate. So it's a stricter metric, strictly larger than the recall rate. And finally, we have identity uniformity, which is how many different which measures sort of the entropy of the recall set. So intuitively, we want a lot of different people to be in the nearest neighbor set of our query photo, right? If we have one query photo of me, you want to make sure it's hard to identify me in the lookup set. So you want lots of other people in the lookup set. And the identity uniformity is defined such that it's 0 when there's perfect entropy. So there's every person in the lookup set is a different human being, and it's 1 when I'm the only person in my own lookup set for a given query photo. So for all of these metrics, it's important to realize that they're all between 0 and 1, and the lower is better. So all of these, the goal of this privacy protecting scheme is to get these as close to 0 as possible. Okay, so our work focuses on 2 different paradigms of defending one's privacy in this sort of embedding space. The first is what we call the individual approach. So let's say you're a person and you want to protect your privacy, and you know that this face recognition company has access to these 5 photos of you, which appear normally in the center. What do? Well, if you can modify those photos of yourself, the best thing to do, the most obvious thing to do, is sort of scatter your photos as far away from their original location as possible. Because when you have a new photo, like this new query photo, it's going to appear close to where your old photos used to be. And since you've moved your old photos, hopefully photos of different people will be the nearest neighbors as opposed to the original photos, right? That's the most intuitive thing to do. And that's actually the proposal of many previous works, is to talk about this line of thinking. The issue with this approach is that you don't have access to all the photos that a company might have scraped of you, right? So if you're thinking about this problem in 2021, it's likely, in fact, highly likely, that a face recognition company has already scraped several photos from your social media and has them already sitting there in the database. And you have no way to modify those photos. So even if you modify all future photos that you put out on social media, there are already some immovable points that you just can't change. And that's going to make this problem harder, right? So we do a quick study on this. We talk more about this in the paper, but we find that if you can modify every photo of yourself in the database, then you're golden. Then it's very easy to drive all metrics very close to 0. Problem solved, with no problem. But the issue is that if you have even, a small number of photos lingering behind that you can't modify, for example, from the past, clean photos that a company's already scraped of you, then this problem becomes much, much harder. And these individual approaches become less and less successful the more photos they have of you. So we need to think about this problem in a slightly different way, with a slightly different tack. And that's the main thrust of our work today. So the goal is to do this on a more community level, to think about how we can protect each other using a large number of decoys, as opposed to just sort of only focusing on our individual privacy and moving our own photos, how we can sort of flood face recognition systems with lots of decoys on the internet. So we have some lookup set, again, an embedding space, and we have some particular query photo. And the goal here is, well, normally without any intervention, right, the top 5 nearest neighbors identify us perfectly. So we want to make sure that the top 5 nearest neighbors are not these 5 photos. Ideally, they would be decoy photos. Ideally, we could find some way to perturb other photos of other people or celebrities or whatever to be closer to the average query photo than the rest of our lookup set photos, right? So this is the key idea of the FoggySight scheme, is to use lots of decoys to predict where new query photos will be, such that the nearest neighbors of new query photos are going to be people who are not us, who can't be used to link back to us, who can't be used to identify us. So there are a couple of different ways to sort of take decoy photos and move them into our space. From a mathematical perspective, we talk about 4 different approaches in the paper, which I'm not going to go into a ton of detail here, but they're listed here. And we do compare against different methods of doing this, although further investigation into this could constitute interesting for future work. So given some decoy, we can see the decoy photos with different levels of modification here. It turns out that we do fairly well at driving metrics low, as long as we can have a lot of decoys. So we compare against the perturbation amounts of the magnitude of the adversarial example on the x-axis, and the mean recall, which is one of our metrics, on the y-axis. And we show that as long as we perturb the images enough, which is still not visible to humans, with a certain perturbation, we can drive this recall rate very low, which is great, which is a success. We do the same with other ways of targeting the lookup set, the mean as opposed to an arbitrary vector. And this seems like a success, which is great. But one thing which is even more important question, which is how many decoys do we actually need? So for some fixed epsilon, how many more decoys do we need than your average lookup set to cloak you, to protect you? And it turns out that depending on the epsilon, depending on the model, you may need anywhere from 2 to 5 times as many decoys relative to clean lookup photos to protect yourself. Which means, let's say, for example, a company has scraped maybe 5 photos of you. You would need upwards of 10 to 25 photos to sort of decoy away from you to protect your privacy, which sounds like a fair bit. And it is, because this is a hard problem. And that's why we're sort of talking about this at the community level rather than the individual level. I'm going to blow through one more result or 2 more results because I want to get through the slides. Here are the other metrics with the same x-axis as last time, the proportion of decoys relative to clean lookup photos. And it's important to note that in this slide and in the previous slide, this assumes a white box model. So this assumes that in some scenario, we know which face recognition model the company we're trying to protect against is using. This is not an entirely unreasonable assumption because these face recognition models are usually public in GitHub, and even if they're proprietary by the company, the architecture that's used is usually from an academic paper, which again is public and on archive. But we also do talk about the white box setting. There are some techniques to modify images even without knowing what model you're attacking. And we use those techniques, but we find that in the black box setting where you don't have access to the proprietary model that a company is using, this problem becomes much harder. So it's still possible to protect your own privacy, but instead of needing 2 to 5 times as many decoys, you might need as many as 7 times as many decoys as clean lookup photos, and you need to make your perturbation magnitude much, much higher. So you need to visibly alter the image a lot more. And this just speaks to the difficulty of this problem. This shows that if a company already has photos of you that are clean, especially a lot of photos, and if that company takes great pains to keep its model private, then protecting your own individual privacy computationally, especially if your computational resources are limited, is a very, very hard problem. And our results show that while it's possible, it's difficult. It's difficult, and we don't want to overstate the difficulty or understate the difficulty of protecting your own privacy. So that's sort of an overview of the FoggySight system. It uses adversarial examples to protect against face recognition technology. And the novelty really is in the way it frames the problem. So previous approaches really focus on this problem as protecting your own individual privacy. But we find in our work that this is a very difficult thing, because if a company already has clean photos of you in their database, then it's almost impossible to defend against any face recognition system on your own. But we show that with the appropriate sort of community level approach, it is possible actually to defend against your own privacy, as long as you use the right targeting strategies, and especially in the white box setting where, for whatever litigation or publicly data access reason, the company's model is available. So that's sort of a quick overview of the FoggySight system. I would encourage you to ask questions now and see our original paper, and also reach out for further questions. After the talk, you can email us and connect us on Twitter. All right, thanks for talking, and I'll see you in the Q&A session.